In this video we are looking at PCB stackup. Why is it crucial in our design, what do we need to know, and what materials are actually being used when we make our boards. So why is it crucial? The stackup itself, it can be easily overlooked. It's something that maybe when we're starting out we don't really pay much attention to. We just really care about how many layers do we want our board, or what's the thickness of the copper, but we don't really look at the layer thickness instead. Should we be worried of what signals we put in, what planes do we put in? Let's take a closer look at it. So what materials are involved here? There's prepreg, copper foil, and copper clad laminates, or otherwise known as the core. As you can see here, we have a general makeup of our PCB and how it's actually formed for a heated press. And what are these materials entirely? We'll start off with prepreg, semi-cured materials that allow strong bonding. So this material goes over here. As you can see, when you select your board layer, it's otherwise known as FR4. Copper foil serves as a conductor in our board, later etched to form circuit traces, and the core. Prepack and copper foils are laminated and cured to form copper clad laminate. So this is the standard makeup of our board. So if we look into here, we see the general, we have our copper, prepeg, and core. Of course we have our surface finish, solder mask, and so on as the outer layers. So if you notice in your whatever ECAD tool, you may be able to select different prepregs or different materials, but what are they? What's the difference between all of them? Well, they can be categorized into high resin, medium resin, standard resin. And because of this, they each have their own resin content, as you can see on the table here. But generally, the higher the resin content, the higher the cost. So please do some research if you're selecting, don't just go randomly clicking them. Now maybe, so what's the effect? Well, one of the effects is that different resins, they have different resin content, they have different dielectric content. So this can affect your impedances if you need that sort of parameter to keep worry of. Copper foil. Copper thickness, purity, copper dielectric, interference profiles. So what are you choosing? Copper thickness, how thick your copper is. In most cases you'd be interested in this for its current handling ability. Thicker copper means more current you can be carried, and for example of this, maybe you wanted 6 amps to go through a trace, and 1 ounce of copper for that trace was too wide, and so you didn't like how it's being routed. It could have taken way too much space on the board. In this case, you might want to increase the copper thickness to allow you to have a smaller width trace. To calculate this, there's loads of online calculators which we'll look at the end of the video, of one I particularly use called Saturn PCB. Copper purity, how pure is this copper? Usually it's the foil is roughly 99%, and copper dielectric interference profile. So in higher profiles, such as this one, the signal travels along contours, which is less than ideal. So actually your signal path, because of the rough edges of that high profile, it kind of goes in this sawtooth way. Not exactly, but it follows along the contours. But ideally we want a straight current flow, so this is when you would opt for a low profile. Of course, if you're just messing around with designs that they're not really high speed, they don't really require certain parameters, your standard by profile one would be fine. But for high speed designs, this is not optimal. So someone may optimize this purely just to get the more low profile one. So what about dielectric materials that go into this? And this one is quite a wordful, so be patient. Let's go through this step by step. Dielectric concept, relative permittivity. So this is the ratio of electric permittivity of the material to the electric permittivity of free space, or otherwise known as a vacuum. It is also known as relative permittivity. So this could be the dk or ER for relative permittivity. You'll see this. And this can range in 2.5 to 4.5 for your PCB materials. This is specifically important when you are concerned about impedance matching and everything of that sort, because the dielectric contents, they do affect your impedances. So if you change them, you'll see it go up and down. This decreases as frequency increases, and high speed boards require lower dk materials for dielectric constant. Loss tangent or dissipation factor. The loss tangent is the phase angle between the resistive and reactive components of the system with permittivity. So essentially your signal degradation. This value ranges from 0.001 to 0.03, and really I think for this also, if you're not doing any high speed RF circuits, we don't need to care about this, but in those cases a low DF is required, because you do not want your signal to disappear over time, as you might not want that. Glass transition temperature. So this is when your board is actually heated. So if it gets too hot, there'll be a point where it turns into this softened, deformed state. So instead of it's rigid, solid feeling, it becomes quite soft and deformed. But when the temperature is reduced, the material goes back to its original state. But I say this, it should not be exposed to higher than its rated TG. As you might know, it's not optimal, it's not ideal. And its decomposition temperature, TD, is when the material decomposes chemically. This is irreversible, so once you've gone beyond this, you're starting to break it down. Thermal conductivity, how efficiently, or how this material conducts heat. Low thermal conductivity means low heat transfer, while high conductivity implies high heat transfer. Coefficient of thermal expansion, your board does expand upon heating, so do keep something that in mind. Moisture absorption, so the ability of your board materials to resist water absorption when immersed in water. As you can already tell, this is something that we don't want, so you relatively want something that is quite resistant, CAF resistant. And this is conductive anodic filament. Conductive anodic filament, I've probably said that wrong, but it is basically a metallic filament formed inside the board material, and you could search this up, and I'll try to put an image on screen. So if your circuit board is going into a high temperature, high power environment, you need to opt for something that is CAF resistant, as the formation of CAF can lead to a short between two conductors, which you already know is quite bad. Tensile modulus, tensile strength, your standard, when you say I'm not mechanical, so I don't even know, measure of mechanical strength of a PCB material. So stress, strain, how strong it is, compression against it, these kind of things. And these become quite critical, I guess, in quite harsh environments, maybe aerospace, or it's going somewhere where the conditions are rough on the board itself, and you want something that's, that can withstand it. So how do we select one? Well, we can categorize our board into these 4 sort of categories. I guess for the most part, if we're just messing around, for at-home stuff, I guess we fall into the low power, low frequency stuff, or it could be anyone, but I tend to only do that. But I'll give you a brief rundown on what's going on. So high power, high frequency. So if you had something like this, the board must be able to tolerate high temperatures, requires effective thermal management. Selecting materials for high power boards, ensure they are of low DF, DK, and high thermal conductivity. And usually when you're working with high frequencies, or in RF spectrum or whatever, you tend to use Rogers, as it's one of the preferred materials for this category. And for low power, low frequency, so our standard stuff, we can just use standard FR4. We're not too bothered about what is it going on. We can opt for higher DK, DF materials. We don't really need anything too expensive, like prices on our minds, essentially. So the importance of a stack up itself. There are many videos out here that will do a better job than this, because it's a whole topic in itself. Again, most people recommend, and I do recommend, is the grounding video by Rick Hartley. But what this is how important it is that having a proper stack can improve signal integrity by reducing electromagnetic emissions, crosstalk, and tighter controlled impedance. So your material selection also, you would think, plays a very, very important part in your designs for this, as I've just stated. As well, your stack up in this, so how you layer your stack up, you can get more issues with it than you expect. So in that video of grounding by Rick Hartley, he speaks about one of his clients. The client had they probably missed a stack up or something, was an agreed stack up, and they found out that their signals they were not getting what they wanted. It was all because of the stack up itself. So you can already see that there is quite a big importance, and we tend to gloss over this, I think, in the beginning stages. I know that I did. You would notice also that this is symmetrical, so you could see that everything is in symmetry. This is because if it was asymmetrical, this is prone to warpage and deformation. So now that we've covered briefly this, I'm going to jump into Altium. I'm going to show you what is going on with the impedances in the calculator, and as well we're going to jump into Saturn PCB as a brief run through. So here in the layer stack manager, we can closely see that all the different values that we have here. Many times when we're just starting out and things, and I tended to do this, is we just go to the presets library if you're using Altium. I'm not too sure in your own ECAD designer tool, but here I'll just select the preset and I wouldn't really touch anything else. This was an issue because many different manufacturers, as said before, they have these different thickness in their different stack ups. So this could greatly affect in your terms of cost or whatever, if can it even be done. Also, I mentioned about the impedance control. So over here we can add impedance profile within Altium itself. I've used this many times in the past and it's done quite well. But of course, you should always trust your manufacturer of choice for their impedance profiles first, as they would know better, and they do this day in, day out. Coming into Saturn PCB here, you can see I have all these different values and I can change them here. So all these different calculators which I use, not all of them, but I use to help me throughout my designs. So let's take, for example, this conductor properties one. We can already see with the conductor width, and for example, if we had a copper weight of micron, you can see here that depending on what we choose here, we can see it go up, and then you can see what we're calculating here. So after changing to 1, we can see the different values we have. So it's quite useful this for us to calculate, and this is something I use quite a lot. We'll different kinds of calculators here, and it's very useful for it. So that was the end of that. I hope you did learn something. I hope everything was good. I hope you enjoyed the video.